Hello and welcome everybody. My name is Tim Schreiter and today I'm going to present to you the THÖR-MAGNI challenge. I'm a PhD student with the Technical University of Munich and we have pretty interesting insights to tell you about our dataset. So on this very first slide here, we can see a short video in which you can see a snippet from our dataset. You see human agents moving in a shared environment with a mobile robot that is navigating the environment as well. Our focus here is on the social human navigation of the people in the scene. Let's first motivate the topic. So the topic is very interesting for our research group ever since this Spencer project, which is on screen right now in 2016, where we asserted how a robot should move to its goal in a very crowded environment, that being an airport. In such an environment, you will find very dynamic scenes and you will have agents of completely different attributes. So our robot should be able to forecast the motion of these people with different attributes. So that'd be like individual people, then people with different attributes like elderly people or people pushing carts, toddler carts, or luggage, and then also social relations in groups. And you should be able to consider these factors and plan its path in a safe and timely efficient manner to the goal point. This topic has spiked of interest in recent years. As we can see, there has been a surge in publications, particularly because this topic got of interest to the autonomous driving community, where it is a safety concern. As such, the need for good quality datasets has grown a lot as well. And in early datasets in this domain, we've a lot of times have certain issues like uniform motion in straight lines or noisy ground truth in the form of the Edinburgh dataset, or in large scale recordings like the Stanford drone dataset, you sometimes have low annotation quality. So these early datasets had these issues, and now modern datasets, autonomous driving, where this is a safety concern, they have a lot of powerful features. That being, they are egocentric and multi-modal. So they have different modality streams like lidar or LHMP data. They are in challenging environments, urban environments, where people can cross the road very unexpectedly. And they include a comprehensive labeling of all target entities that are in the dataset, like pedestrians, cyclists, and other cars. And our objective now is to take these high quality standards from automated driving and take them and apply them to social robotics datasets, where the robots can assert the social human navigation around them and take those to the next level. With this being said, let's think a bit about the requirements that we potentially have for such a dataset. First of all, it should be accurate. It should have a very high quality and accurate ground truth. Then it should be challenging so that our model can in the end learn something more than just constant velocity. It should possess rich motion cues. In the end, preferably more than just walking trajectories, but other contexts of the human motion should be captured as well. And it should possess multimodalities so that our model can learn on multimodalities for having a better understanding of the scene. In that sense, there's already the pioneering THÖR dataset, which was recorded by our research group a while ago. This dataset is available online or using the link that you see on screen now. And what this dataset features is 60 minutes of motion, 3D positions and 6-dot head orientation, alongside with high quality motion capture data and supportive sensory data like eye tracking or stationary lidar and camera data. The third dataset is already applied in research and in industrial applications. For instance, it is used for motion planning in dynamic environments, for casual modeling in dynamic systems, or used for multi-robot task allocation. And furthermore, it is part of the Atlas benchmark, which enables benchmarking of state-of-the-art human motion prediction approaches. Now, going further on this topic, it would be nice to extend on all these aspects that THÖR has laid out and introduce it and update it with a lot of more powerful features, context about the human motion, and a lot of different exogenous factors. With that being said, we introduce you THÖR-MAGNI, which is the newest entry in the THÖR family and is a completely standalone dataset. It is also available for download on our website. And here we have a side-by-side comparison between THÖR and THÖR-MAGNI. And we see that in THÖR, we had just 3 different scenarios with 13 runs that summed up to 1 hour of motion capture data. And in THÖR-MAGNI, we have 5 different scenarios with 2 to 4 runs each and 40 different participants. That sums up to 3.5 hours of motion capture data with supplemental data of 3 eye tracking devices and some mobile robot data as well. So in THÖR, we had the eye gaze data available for 1 participant, the head orientation and the gaze overlay videos. And in THÖR-MAGNI, we provide the gaze vectors for 2 participants and the gaze overlay videos for 3 participants. And furthermore, the 2D gaze coordinates alongside with the trajectories and the head orientation as well. Additionally, modalities in THÖR are the stationary camera, lidar sensor and camera, and in THÖR-MAGNI we have lidar data from the moving robot and onboard sensor data of that very same robot as supplemental information. Now, as for the scenarios that we've recorded, our dataset is structured in 5 scenarios that enable very precise testing of hypotheses and also follow-up research that we cover in our research paper. But to summarize them, we have this very first scenario, which features social walking in static setting with variations. And in this setting, we all have one condition where we only have static obstacles. It's a baseline situation where people just navigate naturally the scene. And then we have another condition where we manipulate the semantic attributes of the environment. We introduce flow markings, stop signs, and one-way passages to simulate the flow of motion of workers in an industrial environment. In our second scenario, we add tasks to the people so that we don't only have visitors, but we also have carriers of objects, so carriers of box and buckets and larger objects. To this end, we already have a really interesting research publication. Please check that out. It's here on screen right now. Then in the third scenario, we investigate the driving styles of a mobile robot and see how the driving styles affect the perception of human motions. This is described in our THÖR-MAGNI paper, and we recently also got a paper accepted to the Roman 2024 that describes how the attention, the visual attention of humans is influenced by these driving styles. And in the fourth scenario, we include, together with the fifth scenario, intended HRI. In this fourth scenario, the robot is actively interacting with participants and goes together with them to goal points, simulating an active interaction as part of an active collaboration on a factory floor. And in the fifth floor, the robot and the participants, they can work together to transport objects from point A to point B. Overall, our dataset comprises of these 5 different scenarios. It's very extensive, and this figures right out of our paper. It provides you with a very sophisticated overview about these scenarios, what is included in each, the layouts, i.e. maps, and the roles that participants took, and how much data was recorded, and so much more. With this being said, this should be the introduction to the other 2 videos of my colleagues that introduce you to the THÖR-MAGNI challenge, where we introduced the benchmark and submitting it to GitHub, where you can evaluate your state-of-the-art motion prediction approaches on our benchmarking code and dataset. Thank you very much for your attention. And now on screen, you see again the QR codes for the paper and for the dataset.